Chapter 1 Real Numbers. First exercise. Express each numbers as a product of its prime factors. Prime factors we can do in different methods. One is that factor tree method. If we are doing that one, factor tree first number is 140. 140 we can split that into 2 into 70. Then that 70 again 2 into 35. That 35 is 5 into 7. So here we are getting all the numbers that is prime numbers. We can write that as 2 into 2 into 5 into 7. Then otherwise the normal prime factorization method 140. First prime number that is 2 divided by 2. Here 70 again by 2. 35. Then next prime number 3. It will not go in that. Then 5. So 7 times again with the 7 1. So 2 into 2 into 5 into 7. Any one method we can follow that. So which is equal to, this is the prime factorization of 140. Which one we can write as 2 is repeated 2 times. So 2 square into 5 into 7. Now second number 156. 156 same way by 2. 78 again by 2. 9 then by 3 divide by 3. 13. 13 is a prime number. So we can write that here also 2 into 2 into 3 into 13 which is equal to 2 square into 3 into 13. Next one is 3825. So 3825 we can divide by 5. 765 again by 5. 153. 3 plus 1 4. 4 plus 5 9. So divisible by 3. 5 times in 15 and 1 time in 3. Again 5 plus 1 6. Divide by 3. We are getting that 3 2 times, 5 2 times and 70 which is equal to 3 square into 5 square into 17. Next one 5005. We can do any one of this method, prime factorization, by factor tree method or by prime division with the prime numbers. Here 5005. We can divide by 5. One time 0 0 1. Here this we can not divide by 2 3 5. Then next prime number is 7. Here 143. Then after that number can divide by only 11. 13 times 11 and 13 are prime numbers, so one time. Here we are getting as 5 into 7 into 11 into 30. Next one 7429. 7429. This we have to check with all the prime numbers. We know that the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, etc. So one by one we have to check with all these prime numbers. Then we can see that first one it is coming 17 only. 17 here when we are dividing 7429 with 17, 437. Then that we can divide by 19, here 23 times. So 23 also prime number. So we can write that number as 17 into 19 into 23. Second question, find the LCM and HCF of the following pair of integers and verify that LCM into HCF is equal to product of the two numbers. So we can write 26 is equal to, when we are doing the prime factorization, 26 by 2, here 13. 13 is a prime number. So 2 into 13. Same way 91. That we can write as by 7. 13. So 91 is equal to 7 into 13. Now from here we can see HCF is 13, the common factor, that is 13 only. So we can write HCF is equal to HCF, that is 13, then LCM. LCM is equal to remaining numbers we have to take 2 into 7 into 13 just one time. That is common in both the numbers, so take one time, which is equal to 2 into 7 into 13 is equal to 182. Now we have to prove that HCF into LCM is equal to product of the numbers. Therefore, HCF into LCM is equal to 13 into 182 is equal to 2366. Product of the numbers. Product of the numbers, which means 26 into 91. That also is equal to 2366. So here we are getting both the answers that is same, 2366. So we can write, therefore, LCM into HCF or HCF into LCM. HCF is equal to product of the numbers. Product of the numbers. Then we can write hence verified. Just to verify that statement, so we left LHS is equal to RHS. LCM into HCF is equal to product of the numbers. Second one, 510 and 92. When we are doing the prime factorization, 510 is equal to 2 into 3 into 5 into 17. 92 is equal to 2 into 2 into 23. Here common factor, that is 2. So we can write HCF is equal to 2 and LCM is equal to, we have to take 1, 2 from the common factor from these two and the remaining terms, numbers. 3 into 5 into 17 into here 2 into 23. Your 2 square is coming, which is equal to 23,460. Now HCF into LCM. Now we got these two. We have to verify this. So we can take LHS. That means LCM into HCF. LCM into HCF, which is equal to, LCM is 23,460, that into HCF is 2, which is equal to 46,920. Same way product of the numbers, RHS, which is equal to, the numbers are 510 and 92. 510 into 92, which is equal to, same, 46,920 we are getting. So we can write LHS is equal to RHS. Then hence verified. Third part, 336 and 54. When we are doing the prime factorization of 336, we will get 2 raised to 4 into 3 into 7 and 54 as 2 into 3 cube. Then HCF means we had to take HCF the lowest one. Power as the lowest one. Here 2 raised to 4, here 2 we can take as 2 raised to 1. So the lowest one 2. Here 3 cube. The lowest power, that means just 1 time 3. 2 into 3, 6. In the case of LCM, they have with the highest power. Here 2, here 2 raised to 4. So for the LCM, 2 raised to 4, 3 cube, then the remaining number, that is 7. 2 raised to 4 is 16, 3 cube is 27, into 7 is equal to 3024. Then we can take the LHS. LCM into HCF is equal to 3024 into 6. We'll get that as 18,140. When the product of numbers 336 into 54, that also 18,114. That is LCM into HCF is equal to product of the numbers. Third question, find the LCM and HCF of the following integers by applying the prime factorization method. So first one, 12, 15 and 21. By prime factorization method, we will get 12 is equal to 2 into 2 into 3, 15 is equal to 3 into 5, 21 is equal to 3 into 7. Here we can see 3 is common everywhere. So HCF of 12, 15, 21 is equal to 3. And LCM of these numbers, we have to take 3 just one time, everywhere that 3, so 3 one time, then the remaining numbers 2 into 2, 5, 7, which is equal to 420. So find the LCM and HCF. LCM is 420, HCF is 3. Second one, 17, 23, 29. We know that all these three numbers are prime. So we can write 17 is equal to 17 into 1. 23 is equal to 23 into 1. Same way 29 is equal to 29 into 1. So HCF of 17, 23 and 29. Except 1, no other common factors, so 1 we can write 1. Then LCM is equal to 17 into 23 into 29, which is equal to 11,339. Third part, that is 8, 9 and 25. 8 we can, by prime factorization we can write that as 2 into 2 into 2 into 1, 9 as 3 into 3 into 1, 25 as 5 into 5 into 1. 1 we are writing because there is no other common factor here. So HCF of 8, 9 and 25 is equal to 1 only, no other common factor there. Then LCM is equal to here 2 cube into 3 square into 5 square, which is equal to 2 into 2, 4, 4 into 2, 8, 8 into 9 into 25, same number, which is equal to, we will get 1800. So LCM is 1800, HCF is 1. Fourth question, given that HCF of 306 and 657 is equal to 9, find the LCM of 306 and 657. We know that LCM into HCF is equal to product of the numbers. Here HCF is given. We have to find LCM, which means from that LCM is equal to product of two numbers divided by product of numbers divided by HCF. that is LCM of 306 and 657 is equal to product of the numbers, which means 306 into 657. These are the numbers. Product means into. Divided by HCF of these numbers, that is given 9. So product divided by HCF. So which is equal to, when we are dividing that by 3, we can divide here 3 times, here 1, 0, 2. One more time by 3 times 1, 2, 34. So 34 into 657, which is equal to 22,338. So LCM of 306 and 657, that is equal to 22,338. Question number 5. Check whether 6 raised to n can end with the digit 0 for any natural number n. We know that prime factors of 6, that is 2 and 3. 2 into 3, 6. Here 5 is not coming. If 5 is there, then only 2 into 5, it will come 10 and unit place 0. Since 5 is not a prime factor of 6, therefore 6 raised to n cannot end with the digit 0. Question number 6. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. First we can consider this one, 7 into 11 into 13 plus 13. This is a product, these three numbers, in between multiplication sign and here addition sign. So this is one term and this is the second term. From these two terms we can take 13 as common. So if we are taking 13 as common from the first term, that means till here we are considering as single term. It's a product. So 7 into 11 is remaining, plus this 13 is taken out, then 1 only there, which means 13 into 7 into 11, that is 77 plus 1, 78. Now we can see that we can write the given number as the product of 2, which means this is a composite number. Or we can again prime factorize 78. When we are prime factorizing, we will get 2 into 3 into 13, which means 2 into 3 into 13 square. So the first number we can write as the product of prime factors. Same way here, 7 from 7 to till here is the product, multiplication sign in between, and here 5. So we can take 5 as common in the first bracket, then remaining 7 into 6 into 5 already we took out, then 4 into 3 into 2, 1 on it, plus when we are taking the 5 out, here 1 is coming, which is equal to 5 into, when we are multiplying all these numbers and then add 1 with that, so we will get 1009. So product of two numbers. Therefore we can say that both the numbers are composite. Here we expressed both the given as that as a product of prime numbers or prime factors. Therefore these numbers both are composite numbers. Seventh question. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point at the same time and go in the same direction. For example, if we are moving like that way, they started from here and going in the same direction. After how many minutes will they meet again at the starting point? Both are taking different time. Sonia is taking 18 minutes and Ravi is taking 12 minutes to complete one circle. So after how many minutes? Which means we have to find the LCM of these two numbers, 18 and 12. 18 we can write as 2 into 3 into 3. 12 is 2 into 2 into 3. Prime factorization. Then LCM is equal to 36. So we can write they will meet each other at the starting point again after 36 minutes. Exercise 1.2. First question. Prove that root 5 is irrational. For that, first we had to assume. We had to prove this is irrational. So we had just to assume that as be a rational number. So let root 5 is equal to P by Q be a rational number, where P and Q are co-primes, no common factor. For that P and Q, and Q not equal to 0. Then when we are cross multiplying, we will get root 5 Q is equal to P. Square it. So 5Q square is equal to P square, which implies we can write P square is equal to 5 into Q square. That is question number 1. Here we can see this P square is divisible by or divides by 5. That P also we can divide by 5. Since 5 divides P square, so it will divide P also. Then we can take let P is equal to 5R. 5R, which implies equation number 1 we can write as 5R square is equal to 5Q square. That is 25R square is equal to 5Q square. Divide by 5, which implies 5R square is equal to Q square. Here we can see Q square also divides by 5. So we can write. So here also we can write, since 5 divides Q square, so it will divide Q also. Here we can see 5 is a common factor of both P and Q, which contradicts our assumption that root 5 is rational. Therefore, root 5 is an irrational number, hence proved. So first we have to take root 5 as be a rational number. So we can write root 5 is equal to P by Q, cross multiply, root 5Q is equal to P, square it, 5Q square is equal to P square, which means P square divides 5, or since 5 divides P square, then it will divide P also. Similarly, here also we will get 5 divides Q square. So that means 5 is a common factor of both P and Q. First we have taken here P and Q are co-prime numbers, which means no common factor. But here we are getting, they have the common factor 5, which contradicts our assumption that root 5 is rational. Therefore, root 5 is irrational. Second question, prove that 3 plus 2 root 5 is irrational. So first we will assume that let 3 plus 2 root 5 be a rational number. That means we can write 3 plus 2 root 5 as in P by Q form, where P and Q are co-prime numbers and Q not equal to 0. So from here 2 root 5, which implies 2 root 5 is equal to P by Q already there on the right side, that minus 3. Which is equal to P minus 3Q by Q. Here we can see P minus 3Q by Q is a rational number. But on the left side we are getting root 5 is there. So root 5 is not a rational number. Already we know that root 5 is a rational number. This we can write just root 5 is equal to 2. Also we can put it down. So P minus 3Q by this 2 will come down, 2Q. This is a rational number and left side is an irrational number, which contradicts our assumption. Therefore, 3 plus 2 root 5 is an irrational number. Here we know that P minus 3Q by PQ, which is a rational number. But we know that left side root 5 is an irrational number. which contradicts our assumption that 3 plus 2 root 5 is rational. First we have taken 3 plus 2 root 5 is rational. That assumption is wrong. Therefore, 3 plus 2 root 5, we can write the conclusion, that is irrational. Third question, prove that the following are irrational. First one, 1 by root 2. Let us assume that 1 by root 2 is rational, which means 1 by root 2 we can write as p by q form, which implies, take the reciprocal, root 2 is equal to q by p. Now here we can see that q by p, this is rational, and we know that root 2 is irrational. So one side is irrational number, the other side is rational number. They both are not equal. So which contradicts the fact that root 2 is an irrational number. Therefore, from that we can write 1 by root 2 is an irrational number. So we can write this contradicts as contradiction has arisen because of our incorrect assumption that 1 by root 2 is rational. Therefore, the conclusion is, we can conclude that 1 by root 2 is irrational. The second number, 7 root 5. Let us assume that 7 root 5 is rational. So we can write, which implies 7 root 5 is equal to p by q form, where p and q are coprime numbers and q not equal to 0. Then this one we can write, which implies root 5 is equal to p by 7 will go down, p by 7q. Here we can see p by 7q is rational and root 5 is, so therefore root 5 also, which is equal. So therefore root 5 also showing that is rational. But we know that root 5 is an irrational number, which contradicts our assumption that 7 root 5 is rational. Therefore we can write the conclusion, 7 root 5 is an irrational number. Here we are getting the right side, p by 7q is rational, and therefore the left side also, root 5 is also become as rational. But this contradicts the fact that root 5 is irrational. This contradiction has arisen because of our wrong assumption that 7 root 5 is rational. Wrong assumption we have taken as 7 root 5 is rational. Because of that, here this contradiction is arisen. This side rational number, this side irrational number, and in between equal to. That's a contradiction. Therefore, we can conclude that 7 root 5 is an irrational number. Next is 6 plus root 2. Here first we can assume that, let us assume that 6 plus root 2 is a rational number, is rational. Let us assume that this is also rational. Then we can write, if this one is rational, which means we can write 6 plus root 2 is the form of p by q, where p and q are coprime numbers. Coprime and q not equal to 0 is the condition. These two are coprime and q not equal to 0. Then from here we can write root 2 is equal to 6. We can move to the other side, p by q minus 6, which is equal to p minus 6q by q. Here we can see this is rational number, and so root 2 also is showing or becoming as rational number. But we know that root 2 is an irrational number, which contradicts our assumption. Assumption is 6 plus root 2 is rational. So that assumption is wrong. And therefore we can write 6 plus root 2 is an irrational number. So here from that we can write p minus 6q by q, which is rational, which implies the left side of that equation, root 2. So root 2 is rational. But we know that this contradicts the fact that root 2 is irrational. We know that root 2 is irrational, but here we are getting root 2 is rational. This contradiction has because of our wrong assumption. The assumption that 6 plus root 2 is rational, which means we can conclude that 6 plus root 2 is irrational.